Okay, so today we're going to talk about measurements in science, and we are going to start off talking about metrics or SI units. And so we will be using metrics exclusively in this class. We won't be talking about feet and inches and things like that. So first thing to remember is that every measurement has a number, which is going to be referred to as the quantity. And it also has the standard, which is going to be our unit. So if we talk about, I measured the length of it to be 5, that's meaningless. 5 what? We need to make sure that we have that unit in there when we talk about that. The other thing is a lot of times in physics, you're going to hear, you're going to see a question worded as, what is the magnitude of the force? And so when it asks what the magnitude is, they're asking for the quantity. And this is going to happen a lot. And students are oftentimes confused by that. They're like, well, I don't know what the magnitude is. The magnitude is referring to the number or the quantity that we're looking for. So later on, we'll get into vectors, and vectors are quantities that have direction and magnitude. And so when they ask what's the magnitude of the force, they're saying, forget about the direction, just tell me what the number is, okay? So then we're gonna just talk about the standard SI units, the length is something we're gonna use oftentimes, and we're gonna measure that in meters. Mass is measured in kilograms, time is measured in seconds, and temperature, officially it's Kelvin, but we will basically be using Celsius. Okay. The other 3 fundamental units, we're just going to kind of avoid these for right now. These 4 fundamental units, meaning that they are basic, they are not derived, and they are directly measured. Okay. And then this idea that all of the quantities are derived from these. So if I talk about volume. So volume, oftentimes people are like, well, I can directly measure volume by pouring water into a graduated cylinder. Well, that's true, but you're measuring length. So when you talk about the volume was 10 cubic meters, well, it's a meter by a meter by a meter. So it's direction in 3 directions. So length times width times height. So you're doing length in 3 directions. If you're talking about speed, how fast is something going? That's distance, which is going to be our length, divided by time. Okay, so we'll go over more of those later on. So coming over here, a lot of times in physics, we're going to be using very large or very small numbers. And so we're going to be using scientific notation. Scientific notation is always going to be in this form right here. You're going to have a number in the front, which we are going to call the coefficient. The coefficient should always be a number that is greater than or equal to 1 and less than 10. So you're going to have a number, a decimal, and then the rest of your non-zero numbers. Okay, and then it's going to be times 10, and then you're going to have your exponent, which is basically your power of 10. And so if you have a negative exponent, you're going to be talking about a really small number. If you have a positive exponent, you're talking about a really large number. Okay, and basically this number tells you how many times to move the decimal. So students a lot of times try to memorize which direction to move the decimal. Oh, if it's negative, I go to the left. If it's positive, I go to the right. Just know that if it's a negative exponent, you're talking about a small number. Well, how do I make this number smaller? Well, the decimal has to go that way. If I want to make this number bigger, decimal has to go that way. Okay, so if I have this number here written in standard notation, and I want to convert that to scientific notation, first I need to get the coefficient. Well, where am I going to move the decimal? If the decimal is not written in a number, it's always at the back, so the decimal is right here. And then I'm going to say, well, where do I have to move it? Well, you want to move it to right here, because you're going to have a number, and then your decimal, and then all your non-zero numbers. So I'm going to have 4.56. Then I'm going to have my times 10. And then how many times did I have to move my decimal? Well, it went from here. So going from here to here is 3. From here to here is another 3. And then from here to here is 2 more. So 3, 6, 7, 8. So I should have 4.56 times 10 to the 8th. For this number here, I have 0.00045, And again, I want to get it into this form right here. So I'm going to take my decimal and I'm going to move it from here to right here so that I have a number between 1 and 10. So I'm going to have 4.5 times 10. And then how many times did I move it? 1, 2, 3, 4 times. So I'm going to have 4.5 times 10 to the fourth, but recognize that this is a really small number. When your decimal's in front, that's a small number. A small number is going to be a negative exponent. So I'm going to have 4.5 times 10 to the negative fourth. Okay? So then we're going to come over here to metric conversions. Okay? And this is going to be a great introduction into dimensional analysis. So first off, I have 46.7. This letter here is actually a letter that's L for liter. Anytime you see a letter all by itself, we are talking about our base unit. Okay, so whether this be M for meters or G for grams, if it's a letter by itself, it is your base unit, and I am starting right here. And then I want to convert this number, this quantity, to this unit. DL. So again, the L here is liters. That's what this is here, liters. So this right here is my prefix, and so I'm going to convert to that prefix, D. And D is right here, which is my deci. So I'm going to go right here. So if I look at my chart here, you can see that deci is 0.1. Okay, and so I can see that 1 deciliter is equal to 0.1 liters. And I hate that this looks like, I'm going to write liter here, liter, so you don't get confused. Okay, so 1 deciliter equals 0.1 liters. So when I'm making my conversion here, I'm going to say 46.7 liters. And this is where that introduction to dimensional analysis is going to come. And then here is my equivalency, that 1 deciliter is equal to 0.1 liters. I have liters here, and I want to convert that to deciliters. So my deciliters is going to go on top. And then my quantity for that is 1. And then on the bottom is going to be my 0.1 liter. I'm going to write liter here. Okay, so my liter here is going to cancel out with my liter here, and I'm going to have 46.7 times 1, doesn't change, divided by 0.1. And when I divide this number by 0.1, I'm essentially going to move the decimal 1 time, and I'm going to get 4670, and my decimal will be right there. Okay. That was kind of a confusing one because of the L at the back there, but let's look at another one here. So here I've got DAG. The G is my unit grams. The DA is deca. And so I can see that deca is right here, and deca means 10. And then I want to go to my mg. The G again is my gram, so I care about the M right there, the milli, and milli is right here. And milli means 0.001. So I can write my equivalencies first. I'm going to start off with decagram. So I'm going to say 1 decagram is equal to, and if I come over here, it's equal to 10 grams. And then I'm going to come over here, I'm going to say 1 milligram is equal to 0.001 grams. Okay. So when I write this out, and I'm kind of running out of room over here, so I'm going to do it right here. I'm going to have 5.3 decagrams. And then I'm going to draw my little train tracks here. I want to get rid of decagrams, so I'm going to put decagrams down here. And I'm going to convert to grams. So grams is going to go on top. And then I'm going to just substitute in my numbers, 1 for deca and 10 for grams. So 10 and 1. Okay. I'm going to see that my decagrams here will cancel out with my decagrams there. Then I'm going to draw my next little track here. And I want to get rid of grams. that's going to go on the bottom, and I want to get to milligrams, that's going to go on the top. Okay. Then I'm going to take my numbers, my 1 milligram, so the 1 goes up here, and then the 0.001 goes on the bottom. Okay, so my grams will cancel out here. The only unit I have left is milligrams. I do 5.3 times 10 is 53, times 1 is still 53, divided by 0.001, which is going to give me 53,000. Okay. Last one, I'm going to go from kilometers to decimeters. Again, the M at the back is my meter. So my prefix is D and K. So my deci, once again, is right here, and that means 0.1. And my K is my kilo right here, and that means 1,000. Okay, so I'm going to write my equivalencies. First, I'm going to say 1 kilometer is equal to, and if you come over here, you'll see it's 1,000. So 1,000 meters. 1 decimeter is equal to 0.1 meters. Okay, so then, extend the page a little bit. I'm going to start off with my 8.37 kilometers. I'm going to draw my train track. I want to get rid of kilometers, so I'm going to put that at the bottom, and it's going to be the 1, so 1 kilometer. And then I'm going to put my 1,000 meters above that. My kilometers are going to cancel out, and my answer so far will be in meters. Draw my next train track there. I want to get rid of meters, so here we are. I'm going to have 0.1 meters, and I'm going to have my 1 decimeter above that. My meter here will cancel out with my meter there. The only unit I have is decimeters. And so if I do this out, I have 8.37 times 1,000, so 8,370 divided by 0.1. So that's going to give me 83,700, and that's decimeters. Okay. All right, second to last thing, sorry. The types of variables, so when we run experiments, and we will be doing lots of experiments when we are in our hybrid model. When we're testing things, the thing that we are testing is going to be the independent variable. Remember that this is the variable that you change. There is only ever should be one independent variable. Then as you change the independent variable, the thing that you measure is going to be your dependent variable. So this should change as a result of the changes that you make to your independent variable, okay? It depends on what you do to the independent variable. This is the one that is probably one of the most important things about experiments is your constants. You should only have one independent variable. And that means that you need to make sure that everything else is kept constant. And so this is where, when you design an experiment, most people make mistakes. They just don't keep things constant. You not only need to keep things constant, you need to know how you're keeping things constant. So when you write your lab reports, you'll have a variables table where you will keep your constants. And your constants are things that you are actively keeping constant. And then the control is what you are comparing to. So as you make changes to your independent variable, you are going to compare the changes that you see to the control. So the control group is what's not getting the independent variable. So it's just something that you're comparing to see how your results changed. Last thing, and this is where people are going to struggle. A lot of people struggle with dimensional analysis. So I'm going to start off with things that you're more familiar with, and then kind of make a little bit of a tougher problem for you right here. So I am 48 years old. How many minutes is that? So first off, you need to recognize what you're starting with. This is what you're starting with. And then what are you trying to get to? I'm trying to get to minutes. Okay, so I'm going to start with the 48 years. So I'm going to write it like this. And you can write it as like over 1. I think that's a good kind of habit to get into starting off, so that you see that whenever you do dimensional analysis or factor label, you are going to be using fractions that you multiply across and then divide by the bottom. So I'm starting off with 48 years. So then you've got to come up with your equivalencies. What do you know? Well, we need to get rid of years. So what do I know about 1 year? Well, I know there's 365.25 days in a year. If I count the leap year, okay? So when I look at this, I can write this in one of two ways. I can say 1 year over 365.25 days, or I can write it as 365.25 days over 1 year, okay? And it really depends on how I'm trying to convert this number. If I'm trying to get rid of years, my years from here needs to be on the bottom, okay? So I'm going to put it as this. I'm going to have 365.25 days per 1 year, okay? So when I come over here, I've already written that out. So now I can see that I have years here and years here. So those are going to cancel out. Okay, so when I do this out, my answer will be in days. So then I've got to come back and say, well, I need another equivalency. I need something about days. So I know that each day is equal to 24 hours. Okay. Once again, I can write this in one of two ways. I can say 24 hours per day, or 1 day per 24 hours. I want to get rid of days, so days needs to be on the bottom, and hours is going to be on the top. So once again, I have days here and days here. They're going to cancel out. And now my answer will be in hours. So if I multiply all this out, my answer will be in hours. So now I have one more equivalency that I'm going to have to do, and that is that I have something I know about hours. I know that every hour is equal to 60 minutes. Okay. So once again, I need to figure out how I'm going to write this equivalency. If I have hours here on the top, I want hours on the bottom. And so I'm going to have 60 minutes per 1 hour. This is going to be my final cancellation, that hours here will cancel out with hours here. And my answer will be in minutes, which is what I wanted my answer in. So now I've done everything right because my units tell me that I did it right. And then I've just got to go through and do the math. This times this times this times this divided by this. Well, everything down here is 1. So it's just an easy way of just multiplying out. And you come up with, I'm pretty old. Okay. So then we come down to one that's a little bit tougher. So this is one that you probably could have done in your head. And I would say, please try not to do it in your head. You should use the easy ones to build the skills that are going to get you to be able to do the ones that are a little bit tougher. Okay, so practice this method with ones that you know, so that you can build that skill, so that you can answer ones that are a little bit tougher. And this is, again, this is kind of a mid-level one. So start off, what am I starting with? If a car was traveling 70 meters per second, that's my starting point. And then what do I need to get to? I need to get to kilometers per hour, okay? So when I look at my units, meters, kilometers, I have to change that. Seconds, hours, I have to change that. So I'm going to start off first with my 70 meters per second. So one thing is understanding how to write this. So that 70 meters per second is going to be written like this: 70 meters divided by 1 second. Okay, that's where the meters per second comes from. Okay, it's a distance divided by a time. So I can approach this in a couple of different ways. I can try to change this seconds to hours, or I can try to change this meters to kilometers. For me, I always just like to start with the top and then work my way to the bottom. So I'm going to change this meters to kilometers first. So I need to have an equivalency. What do I know? What do I know about meters and kilometers? Well, if I went back to that prefix sheet on the previous slides, I'd know that there are, and I shouldn't have written it this way, I should have said there are 1,000 meters per 1 kilometer. Okay, so kilo means 1,000, so that's where the 1,000 meters is. So then I'm going to take this equivalency and I have to figure out how I'm going to write it to convert that meters there to kilometers. Well, if meters is on the top and I want to get rid of it, then meters has to go on the bottom. And then my kilometer goes on top. So if I plug that in, I'm going to see that 1 kilometer per 1,000 meters. So meters here, let's cancel those out. So now I have, my answer will be in kilometers per second. Kilometers per, oops, now I got to switch this one, okay? So I'm done on the top though, so I'm good there. And now I just have to focus on the bottom. Well, what do I know about seconds? I know that there are 60 seconds in every 1 minute. So again, how am I going to write that here? Well, here seconds is on the bottom. I need to get rid of it. And so it's got to go on the top. So the 60 seconds is going to go on the top and the 1 minute will go on the bottom. Okay, so here I have my seconds and my seconds, they will cancel out. My answer is in kilometers per minute. Okay, I still want kilometers per hour. So I need one more equivalency to make my conversion. And I'm going to say, well, I know that there are 60 minutes in every 1 hour. How am I going to write this here? Well, minutes is on the bottom. I want to get rid of it. So minutes will go on the top and hours will go on the bottom. And then I can see that my minute will cancel out my minute. My answer will be in kilometers per hour. Kilometers per hour. That's exactly what I wanted. So now I just have to do the math, multiply these numbers together, divide by the multiply these numbers together, and I come up with 252 kilometers per hour. For some of you, that was very simple and easy, and others of you are going to struggle with this. So hopefully this video helps. And again, if it doesn't and you're struggling with this, this is what we're going to be using throughout the year. And so we really need to get this down. So again, these easier problems, write them out. Get that skill down so that you can do the tougher ones as you go. Okay? All right.